Thank you for the introduction. Good afternoon, everyone. Today I'm going to talk about why does your data leak in the cloud from the perspective of mobile apps. And this is a joint work with my advisor, Dr. Zhiqiang Lin, and our collaborator, Dr. Yingqian Zhang. And for the past few years, we have witnessed numerous data breaches. For instance, in 2017, 6 million Verizon user data got leaked from Amazon S3 storage. And Pentagon also exposed some secret data from Amazon server. And data leakages didn't get stopped, and we keep observing them recently. Why does data leakage keep happening? To answer this question, we start from understanding the relationship between mobile apps and their backends. And as of today, many apps use cloud services as their backends. And those cloud services are known as the mobile backend as a service. In short, MBaaS backends. And there are many MBaaS cloud providers like Amazon AWS, Google Firebase, and Microsoft Azure. In our view, data leakage is essentially an access control problem, which regulates which user can access which resource, such as Bob can only access his own data, but cannot access Alice's data. And in particular, access control consists of two procedures here. Authentication that verifies the identity of a user, typically by username and password. And authorization that defines the relationship between users and the resources. So how does access control works for mobile backend, particularly for the MBaaS cloud backend? And for cloud backend, there are two types of users: normal customers for the mobile app and app developers. For normal customer for the mobile app, see user A. She needs to provide an app key to tell the cloud which app sends this request, as well as her credential for authentication. And the cloud will grant her permission based on the configuration file that is defined by the developer to access resources. And since this app key is used for the cloud to dispatch a request to the corresponding backend, so another user for the same app, see user B, she needs to provide the same app key, but with her own credential. And when a developer tries to manage the cloud, she needs to provide a root key to tell the cloud she is the manager. So in short, there are two types of keys, app key and root key. In this study, we focus on three mainstream cloud providers: Amazon AWS, Google Firebase, and Microsoft Azure. And we have discovered two root causes of data leakage. The first is misuse of various keys in authentication, which has been discovered in Microsoft Azure and Amazon AWS. And another one is misconfiguration of user permissions in authorization, which has been discovered in Google Firebase and Amazon AWS. Let me explain them in the following. The first, key misuse. Please recall that there are two types of keys for mobile backend: app key and root key. Let me show you some examples about those keys. The first example is for Microsoft Azure storage, and the first line in yellow is a root key, and the second line is an app key. And developers should put this SAS key into the mobile app and keep the account key privately. The second example is for Microsoft Azure Notification Hub. The first line in green is an app key, and the last one is a root key. And we can see that the app key and the root key, they are in different formats. For other cloud providers like Amazon AWS, the app key and the root key are the same. Regardless of the formats of app key and root key, there is a possibility that developers may misuse of these keys. They may put the root key into the mobile app, which means with reverse engineering on the mobile app, developers can easily get the root key to access all the resources of this backend. And the second root cause is misconfiguration of user permissions in authorization. After authentication, the cloud will grant user permissions based on the configuration file that defines by developers. And lack of configuration or incorrect configuration will lead to data leakage. Let me show you an example of correct configuration for Google Firebase database. Please imagine the database as a JSON file. The name of the root node is users, and the name of each child node is an UID. And the content of the child node is users' private data. And this configuration file enforces that a user can read and write the child node only when her UID equals to the node name, which means Bob can only access Bob's data. And here are two examples of incorrect configurations. The left one indicates anyone can read and write the database, even without login. And the right one indicates any authenticated user can access the database. No matter Bob or Alice, they can directly access the entire database. Obviously, misconfiguration can lead to serious data leakages. Given those observations, our next question is how to automatically detect the cloud leakage vulnerability at a large scale. And to do so, for a given app, first, we need to get the keys from the mobile app. Otherwise, we are unable to locate the corresponding backend instance. To do so, the first question is how to systematically identify various keys used by mobile apps. Since we know the app talks to the cloud by invoking cloud APIs that are provided by the cloud provider's SDK. So in their SDK, there must exist a cloud API that takes a key as parameter. So we can identify the keys by locating such API. But we cannot directly get the value of the parameter. So the second question is how to identify the relevant key strings that are used by the mobile app. And we know the keys are strings, so we can apply value set analysis, try to obtain the content. But there is a considerable number of apps are obfuscated, so we have to make our tool obfuscation resilient. Finally, to detect the vulnerability, the most straightforward way is use the key to access other users' data. But obviously, that violates ethics. So we have to design an approach to detect the vulnerability without access any other users' data. So to deal with those questions, we have designed and implemented a system leak scope. And this is the overview of our system. And it consists of 3 components: cloud API identification that takes APKs and cloud APIs as input to identify the cloud APIs that are used in the mobile app. And stream value analysis that tries to get the content of the key. And then vulnerability identification that use the key to detect the vulnerability. Let me go through those components one by one. First, the cloud API identification. The cloud API that takes a key as parameter are well documented. We carefully read all the documentation from all the cloud providers and found all those cloud APIs. Each of them will take a key as parameter. And to deal with the obfuscation problem, we have implemented a hash function to generate signatures for those cloud APIs and all the functions in the mobile app, and match those cloud APIs with the function in the mobile app by comparing their hash value. The algorithm is well explained in the paper. Please take a look if you are interested. Having identified the cloud APIs that use the key as a parameter, next we need to get the value of the key. To do so, there is a popular technique named the value set analysis. But in our case, we only care about strings, so we have implemented a value set analysis. And I will not go to details here. At high level, this component works first by performing backward slicing to get all the information that used to generate the parameter. Here is the V1. And then repeat the generation procedure to get the strings. After we got the key, we have to detect the vulnerability without access other users' data. Here, we will use a set channel approach by requesting a non-existing data. Since this detection is cloud-specific, we have to apply different strategy for different cloud providers. But the basic idea is the same. We will use the key, send a request to access a non-existing data, and identify the vulnerability based on the return error. If it says unauthorized operation, then there is no vulnerability. And if it says data does not exist, which means we have passed the key check or the permission check, then there is the vulnerability. And please be aware that before launch this test, we first collect all the return errors. And so given a return, we know it's unauthorized operation or data does not exist. To evaluate our system, we applied it on 1.6 million mobile apps and found more than 100,000 of them are used those 3 cloud providers. And around 20% of those mobile apps are obfuscated. And here are some results of the cloud API identification and string value analysis. From the last column, we can see that the string value analysis module can get most of the keys. For the vulnerability detection, in total, we detected 6 different kinds of vulnerabilities. And the first 3 in yellow are key misuse vulnerabilities, and the rest are misconfiguration. And in total, we found more than 15,000 mobile apps are vulnerable. And some of them are very popular. You can see that the vulnerable apps even have more than 100 million installs from Google Play. Having identified those vulnerabilities, we first disclosed them to the cloud providers, and they all took this seriously. Further, they notified all the related developers. In particular, Microsoft immediately cracked the wrong documentation. Actually, they used the root key in their running example in the document. And for Google, they plan to provide a more user-friendly tools when configuring user permissions. And interestingly, for Amazon, they added a new permission checks with its S3 storage before we disclosed our details to them. And here is how Microsoft cracked their documentation. And this is the new updates from Google last month. And you can see they already provide some useful tools to help the developers make their apps more secure. And for the sake of time, I will skip the related work. Please find them in our paper. To summarize, In this work, we have designed and implemented a static analysis system to automatically detect vulnerability, data leakage vulnerability, by performing a cloud API identification, stream value analysis, and vulnerability identification. In total, we found more than 15,000 mobile apps are vulnerable. Responsible disclosure were made to the cloud providers. And we have open sourced our system. Please check it on GitHub. And in this work, we only scratched the tip of the iceberg of the security of cloud-based backend, which is the MBUS backend. And what about others? What about their software stacks, like operating systems or network stacks? Furthermore, what about other vulnerabilities like secure injection or cross-site scripting? Following in this direction, we did another work recently and found much more security issues. And we are going to present this work in the upcoming Usenix. Thank you for the attention. I'm ready for the questions.
Thank you very much. We have 2 mics up front. If anybody has any questions, please come forward.
Luke Bezataus from Samsung Research America. Thank you for the talk. This is a very important problem. I'm a little, let's see. So you sort of push this blame onto the cloud providers, but
yes.
My understanding is that the app developers really should not be putting any key of any sort in the app in the first place. And I just wanted to clarify that, or if you could explain what they should be doing as a best practice. Is this really, I don't know. My awareness is that AWS tells people not to do this, and the developers are doing it anyway. Can you clarify what the developer should do instead?
Yes, you're right. So the fundamental problem of this vulnerability are developers make mistakes, but the cloud providers, they can provide more useful tools to shrink the space that developers can make a mistake. Of course, we hope developers can have secure mind, but that depends. We have to try our best to make the system more secure. Thank you.
Okay. And
Yeah, we have time for one more question.
Thank you. I have a second question. Let's see. You looked into these 3 popular cloud service providers.
Yes.
But if you look for other services, you're going to find a lot more keys. I'm sure that this is happening on a huge scale. Do you have plans to do more generic searches where you don't have a specific cloud provider in mind, you're just looking for the key and then maybe seeing which keys are most popular? And I guess a more general way to find this problem for unknown API providers.
Yeah, in this work, we identify the cloud API by the SDK in the mobile app. So to do so, first we have to collect as many SDK as possible about those providers. So if we can manually do that, of course, it can be done. Just add the target cloud APIs with the keys, then we can get all the content. Thank you.
Let's thank the speaker one more time.